All right, so finally we have defined the complex conjugate, and part A asks what is the geometric interpretation of z bar. So just as z was or could be defined as x plus iy for x and y real and I squared being -1, we can also associate z with the ordered pair x comma y. Because the complex numbers are really identical, or I guess isomorphic, to r cross r, which is exactly what an ordered pair is. It's just one real number and then another real number kind of grouped together. And so logically then the complex conjugate is going to be identical, okay? But remember that z bar is equal to x and then minus I times y. And so z bar would go with the coordinate pair x comma -y. Because I itself can't be positive or negative, but you can multiply it by a positive or negative, and then this imaginary part would have that sign. Okay, and so the geometric interpretation is that if I have some point, it doesn't really matter where, maybe it's this point, for example, and remember that the x-axis is the real part of z, and the y-axis is the imaginary part of z. And if we said that this was z, it has coordinates x and y, which we can denote like this. We can say that this is maybe the x coordinate and the y coordinate. Then we can associate and maybe think of this as the magnitude of z. And then the complex conjugate would essentially be a reflection over the real axis. Okay, so it's going to be the exact same thing right here, but this would be the location of z bar, where it has the same exact x coordinate, okay, but the y coordinate would be opposite in sign. It would be reflected. And so the magnitude of z bar would be the exact same, because you would again be taking the real part squared plus the imaginary part squared, which is equal to x squared plus y squared, which is just the magnitude of z, but the geometric interpretation is just a reflection about the real axis. All right, show that the modulus of z squared is equal to z times z bar. This is actually a pretty easy exercise, but it's a very important one because this is probably a fundamental property of complex numbers. So again, we're going to go ahead and say that z is x plus iy. And likewise, that means that z bar is going to be x minus iy. So if we multiply those together, we get z times z bar is equal to x plus iy times x minus iy. And then we essentially get what we can think of as a difference of squares. So we have x squared minus I squared y squared, but remember that I squared is -1, so minus I squared is really just going to be a +1. So this is going to be x squared plus y squared, which is the modulus of z squared. All right, part C, prove that if z belongs to the unit circle, then 1 over z is really just the complex conjugate z bar. All right, so using part B, we first have to figure out what this statement means. What does it mean for z to belong to the unit circle? Well, it means graphically, if we have the real part of z here and the imaginary part there, the unit circle is going to look something like this, and we're saying that the complex number z is just some arbitrary point on there. Well, remember that the radius of this unit circle, or I guess the equation rather, was x squared plus y squared equals the modulus squared. And so if z belongs to the unit circle, this equation has to read that the modulus of z squared must equal 1. Okay, so then very simply what we have is we have that the modulus squared is equal to 1. But by part B, the modulus squared is really just z times z bar. And since z belongs to the unit circle, it's safe to assume that z can't possibly be 0. Okay, because in an earlier exercise, if z were equal to 0, that implies that the modulus would be 0, and the modulus isn't 0. And so we're safe to divide both sides by z, and then we get the result that 1 over z is z bar.